Thank you very much. My point will be very simple. If we are, as humanity, to address the challenges of sustainable planet, we need, one of the prerequisites that we will need is to ensure that humanity is properly educated, because there will be no rational judgment and therefore no rational decision, especially about the future, if we are not able to consider the objective data properly, and that requires a world which is better educated in terms of being able to read, to do mathematics. If I could have the first slide. So my goal today is to try to show you that it is possible to begin to bridge from neuroscience to education, and that by trying to understand how the brain works, we may begin to have a better handle on the problems of educating the whole of humanity. There are currently millions of children that do not have access to education. There are millions of other children that have access to education but do not get much out of it, do not get enough to be fluent readers or fluent calculators or mathematicians. And can we change that by understanding how the brain works? So, this is the place where I work in France, and as you know, there are many tools now to study the brain. The brain does consume energy, and we can measure the consumption of energy, glucose, and so on through tools like functional imaging, functional MRI, magnetoencephalography, and electroencephalography are ways to get access to the electrical and magnetic aspects of brain function in real time, and in rare cases, for the human brain, but much more frequent for the animal brain, we can go inside the brain with depth electrodes. This is done in humans for epilepsy cases, and in this way we can get access to the insides of the brain. I want to stress that all of these techniques are now being available for young children, so that it is possible to study how the brain is organized and reacts as it is being educated. So these are photographs from the lab where we can routinely host children between the age of, starting at the age of 4 years old, where they can be trained to sit still in this magnet. They are being told that they are the captain of a spaceship, so they collaborate with us. They are told that they should not move, otherwise the spaceship will not work properly. They can click on buttons, listen to stories, and be generating good data from their brains. It is important to note that it is even possible to do so in perfect ethical conditions, even in very young babies. So this is a 2-month-old baby being imaged in the lab, like a little cosmonaut. He's being prepared, protected from the noise of the EMR, and put in a special chair that will prevent some of his movements. Of course, these are individuals who can still react and complain and cry, in which case we may stop the experiment. But we do get good data from even 2-month-old babies, and it's possible even now to do brain imaging in the womb, in the fetus. And there are other techniques, and you see how this is my nephew, who's very happy to participate in this experiment with EEG to measure the electrical aspects of brain activity. So what have we found? Well, the first thing is we can see the remarkable process of structuring of the brain. What you see at the bottom here is the folding of the cortex, which is quite particular to the human primate. And the folding takes place in the last trimester of gestation. So this is before birth, what you see at the bottom, the folding of the brain. The brain is highly organized right from birth. All of the major bundles of connections are already in place, and these already form circuits that we can see are being active. What you see in colors on the left side are networks for language, which if we play language to 2-month-old babies or even to newborns, you already see the channeling of this information to language networks in the infant brain. And there are not only neuroscience experiments, but also very good behavioral experiments suggesting that babies possess intuitions, or what has been called core knowledge, for the major domains of knowledge: numbers, space, probabilities, knowledge of how objects behave, how people will behave. These are different faculties of the brain that are already present in very young infants. So we have a foundation which is not at all a blank slate, and that must be used for education. This is perhaps the first message, that we have strong intuitions in young children. Now, of course, the brain is modifiable. And I think you have all heard about brain plasticity. Plasticity is the ability of synapses, the junctions between neurons, to modify themselves in the face of ongoing activity, which may be partially imposed by the environment. One idea about brain plasticity is that there are different waves of plasticity, which you can see here, and the proposal is that plasticity is not the same in different systems. Sensory systems, like the visual system, tend to have plasticity early on, but it is closed relatively rapidly. For higher level systems, like lexicon or syntax, the plasticity may remain later, but the postulate, as shown in this slide by Werker and Hensch, is that there are windows of plasticity, so-called sensitive periods, during which the brain is better apt at capturing external regularities. So I want to show you one domain which is extremely clear, where plasticity is extremely early and then closes. This is the case of learning the phonemes of your language. You know that in different languages we use different consonants. For instance, Japanese do not hear very well R versus L. I'm French, so I don't hear the difference between da and da, which is different phonemes in Indian languages. So what you see on this slide is that we have a continuum, physical continuum of sounds, and we can ask whether babies and adults discriminate da from ba or da from da, okay? What has been found is that early on, babies are equipotential. They can learn any of the languages, and they discriminate all of these consonants. And we can measure that by habituating them to a series of da, 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 and show that the brain reacts to a novel change of consonant, da, 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 ba, okay? But what is striking is that at the age of 12 months, they lose this ability, and now they converge only onto their native language. So if a baby is in an environment where a particular consonant is not used, such as the distinction between da and da, well, the baby will lose this ability. I think this is a good example that shows, together with a lot of data, that for foreign language learning, if we want people to master a second language, we need to start extremely early on. In the case of consonants, it starts in really the first year of life. In the case of having a foreign accent, it's a matter of having learned after just a few years. We see a decrease in potential, and the decrease is really drastic at puberty, but starts early on. So this is a strong case from neuroscience that we should have language education very early on. Now, this diagram, I think, is a caricature. And the real diagram is more like this. So I correct my colleague's diagram, because plasticity never closes. Plasticity is not completely closed, and it remains open in adults. It's just slower. And also, it can be reopened. So we have studied, for instance, the case of children who are adopted, such that they completely leave their country, they lose their original language, they have to learn a new language. Adoption is such a change that it reopens the brain plasticity, and children will be able to learn very fluently the new language, but they will lose the first one. So there are cases of reopening of brain plasticity, and a strong challenge for our field is, can we do this in schools, or can we do this also with patients that have brain lesions? I want to show how remarkable brain plasticity is, and this is a slide I borrow from Antonio Batro, our colleague, who I think would have shown this if he could have been here. This is the case of Nico, one of the children that Antonio studied. Nico, as you can see, had hemispherectomy at the age of 3, when he was 3 years old. And an entire hemisphere, almost entire hemisphere, was removed because it was severely damaged and had to be removed. But that means that Nico had, at the age of 3, to do his whole school years without the right hemisphere. And the remarkable aspect is that Nico has developed beautifully, got a degree, became a fencer, was able to be on the fencing team for Spain, and also became a wonderful artist. You can see this is not the original, this is a copy by Nico of Impression Soleil Levant by Monet that he made when he was a young teenager. This is 2 self-portraits. One of them, quite interesting, is inspired by Dorian Gray, so one part of the face is not normal, as you can see. He's quite aware of his difficulties, but he's been able to overcome these difficulties, and personally, I wish I was an artist as gifted as Nico is, without the right hemisphere. Forget what you've heard about, left brain, right brain. It's all very caricatural. Here is a case where plasticity is sufficient that the networks of the left hemisphere sufficed to squeeze in much of what needs to be learned at school. So we are navigating between the constraints of early brain organization, but the addition of plasticity, which allows us to overcome strong disorganization. And Antonio published this book, says half a brain is enough. It's better to have 2 halves, but half is good enough. So how do we navigate between this? We have the strong constraints inherited from evolution, neural maps that are present early on in infancy, and bias learning. My claim is that we can have cultural learning, such as the acquisition of reading or mathematics, because there is enough plasticity in specific circuits for them to be recycled. So I compare education to a process of recycling circuits of the brain. And this means that it's not a blank slate. There is a very strong influence of existing brain constraints on the cultural forms and their acquisition, and we have to take into account the organization of the brain when learning. So this idea can apply to many different domains. This is an example from mathematics. On the left side is the monkey brain. Already in monkeys, we know that the intuition of numbers is present. And these are a set of remarkable findings by Andreas Nieder and colleagues, that there are circuits of the monkey brain that care about how many objects are present, a concrete sense of number. Not really mathematics, but we may say perhaps proto-mathematics. On the right side is the human brain. And what you can see is that in the same homolog spots, when we do abstract arithmetic, the same homolog area will activate. That is to say, when we do 3 + 2 with Arabic symbols, we still use circuitry which has a long evolutionary history, but now has been recycled to do exact abstract mathematics. And it goes all the way to high-level mathematicians. Recently, we did this study where we scanned professional mathematicians. When they are doing high-level mathematics with high-level expressions, you can see that the circuits in red for high-level mathematics are the same as the circuits for number processing and calculation in those of us who are not mathematicians, in everybody, basically. So we capitalize on existing circuits, we progressively reconvert them in order to absorb higher concepts and higher symbols. I want to speak about the other example, which I think is the best understood one at the moment. All of this is recent and not fully stable data yet, but the example of reading. Reading is a case where we start with a very organized system for spoken language, but we are able to connect this system through a new interface, vision. Nothing in evolution prepared us to have language through vision, so what we do is we start from visual cortex and we essentially recycle a part of the cortex that will become the visual word form area, a region that specializes for recognizing words. And this is the whole process of learning to read, is to make this area specialized. At the beginning, it is involved in recognizing objects, faces, landscapes, and now it needs to be specialized for recognizing the shapes of letters. So this is the process of learning to read. And in order to do that, you have to connect the letters to the corresponding representation of phonemes in the language system. So this is a sort of cartoon view of what is happening when you learn to read, but we can flesh it out by scanning young children. This is recent data where we scan children before and after the process of learning to read, what you can see is that when you are a 6-year-old and you've just started to learn to read, there is an area of the brain in green that begins to respond to written words, and we cannot find such a response before in 6-year-old children who have not yet learned to read. It will develop and grow and becomes a very strong response, very easily detectable in any of us in this room who have learned to read. This ability to detect the reading system can be very useful, and I think there will be more of this in the future, to detect children with difficulties. If they have difficulties of dyslexia, then we will detect that the area in green that should respond to word is not developing properly in 9-year-old children. And interestingly, we will also see that the reorganization of this visual system is not complete. And for instance, the face system is also disorganized. So when we learn to read, we need to make space for reading by pushing the face system aside, and it moves to the right hemisphere. Well, this is not occurring properly in dyslexic children. And so just by scanning what happens in their brains when they look at faces, we can tell that they are having a problem in learning to read. This is just one example. There are many such diagnoses. I think the prospect of being able to diagnose children, perhaps not with fMRI, but with simpler techniques like EEG, will become an important component of future rehabilitation. Diagnosing children better because we know better what's going wrong in their brains. Now, we can even follow individual children now. This is an unpublished study. We have had ethical permission to take some children and scan them every 2 months. Okay. So we have now 7 scans across the critical year where they are learning to read. And we can see the same brain moving from not responding to written words or responding very little, and then school starts, and we begin to see these responses to written words growing and reaching, as you can see, the frontal lobe, connecting with language representations, and becoming very stable. And then they shrink a little bit as you automatize the process. The process of automatization 1 year later is extremely critical because it means that you can free the resources of the prefrontal cortex and move to higher level aspects of the message of what you are reading. So in education, there is always this process, first of learning something effortfully, and then automatizing it to liberate, to free the resources for new acquisition, and then automatization. The process of automatization, I think, is a key component. Many children are just slow readers, and we hope we can help them become faster readers. Now, one more thought. We can look at this process in adults. And this is an image of what has been transformed in the brains of adults who have learned to read or who have not learned to read. So what we did here is we scanned people that were not literate. They did not have the chance to go to school. Okay? And we can make a difference, image, between those who have and those who have not been to school. What you see here is a very simple image of the responsivity to written sentences. So we can see what I was showing you before, the whole network of areas that respond better because you have learned to read. And they start in the visual system. I don't know if I can point. Here is the occipital pole with responsivity to letters even very early on in the cortex. This is the visual word form area. And then all of this left hemispheric language network, Broca's area here, becoming responsive because you have been able to decipher essentially these marks on paper. The important aspect of this image here is that even ex-illiterates, that is to say adults who did not go to school but learned to read when they were adults, they begin to be on this track. They have strong activation here if they reach a certain score of reading. So we can change the adult brain, not just the child's brain. It's more difficult to change the adult brain, so we should have early education, should invest in early education. But we should also not be discouraged because it is possible to achieve these results also in the adult brain. And in the adult brain also you can see changes in the auditory cortex. So I guess I won't have time to explain this too much, but it's not just the visual system, but also the spoken language system, which is being changed by learning to read. Learning to read also multiplies your memory dramatically. If you ask an illiterate person to repeat pseudo words, They are able to do that for 3 pseudo-words, perhaps. We can do 6 because we've learned to read. So there are huge differences caused by the acquisition of reading. One idea is that we may motivate people, groups, but also governments, perhaps, by showing them how important is this effect of reading on the brain. Even connections are being changed by learning to read. So now what you see here is different people that vary from 0 reading ability, illiterates, all the way to very fluent readers. And if we ask what is different in the connections of the brain, the anatomy of the brains, we can see that some of the pathways, especially linking from visual to perhaps more phonological representations, are different. So reading literally changes the anatomy of the brain. So we have begun to produce summaries of this research for educators, and there are very simple messages that are convergent between neuroscience and education. And one of them is that the key circuit is known now. It's the circuit that converts letters to sound. It's the first one that needs to be put in place, and there is now a wealth of experimental studies in education showing that children who are taught first letter to sound correspondences learn better, learn faster, even when the task is to understand the message, which of course is the final goal of learning to read. So we begin to know what is the easiest way to create these changes in the brain, and we know what should be prioritized, and for instance the fact that once you prioritize this pathway, children can self-teach new words because they can decipher their sounds, understand what that sound means because they have a spoken lexicon, and then automatize this most direct pathway. So after you've put in place the seed of deciphering letters to sounds, children just have to routinize the reading process by reading and reading more. Reading develops through reading. Cognitive neuroscience can inform teaching, and we now have a set of very explicit recommendations for how reading should be taught by explicit grapheme to phoneme conversion rules. There is beautiful research suggesting that we should keep on writing, and that writing at the same time as learning to read is a key component that helps children. Careful guidance of attention from left to right, because it is not obvious to young children that there is a correspondence between the space of the written word and the time of the spoken word. Systematic pedagogical progression, so we can analyze a language and derive from the statistical analysis what are the phonemes that are most frequent, what are the correspondences between letters and phonemes that are the most regular, start with this and create a pedagogical progression, give of course feedback to children about their errors. And there are also a whole array of additional neuroscientific discoveries that concern simply how we learn better. And I should say one very interesting component of this science of learning is sleep. We don't realize that, but during sleep, the brain is practicing. We are not practicing, but our brain is repeating the messages that it got during the day. This is now becoming a really deep neuroscience finding. There are micro patterns of spikes that are repeated during sleep. And there is also direct empirical evidence that improving sleep can lead to a very strong improvement in education. And there are some children that look like they have attention deficits, but they have in fact sleep deficits. And if you improve sleep, you improve the attention, you improve the learning.
Could you try to come to some conclusions?
Sorry if I'm being too long. This was exactly my last slide, actually. So what I would like to conclude with is to say that there are a number of efforts throughout the world now to take this knowledge from the lab into the world, then create bridges first by teacher training, but also by developing devices that may help children acquire their knowledge properly. And my last slide was actually to mention what is happening right now in Africa. There is a very big international competition for the development of tablet devices that could be given to young children in places where there is no good access to education, such that just by using the software on the tablet, you may develop an acquisition of reading and of mathematics. So thank you very much for your attention.